What if I told you that right now, at this very moment, a telescope floating 1,000,000 miles from Earth has pointed its golden eye at a tiny dot of light, and what it found inside that dot has shaken the entire foundation of human science? Not a hint, not a guess, not a theory debated in lecture halls, a signal, a real, measurable, undeniable signal coming from a world orbiting another star, a world that sits in the exact zone where life as we know it can survive. Nobody's talking about what this actually means, but you are about to find out. There's a question that has haunted humanity since the first person looked up at the night sky and felt the weight of the stars pressing down on them. Are we alone? It is the oldest question our species has ever asked. Philosophers asked it, priests debated it, scientists modeled it, and for thousands of years we had absolutely no way to answer it. Not because we lacked curiosity, but because we lacked the tools. We were blind. We were looking at the universe through a keyhole and calling it a window. Then, on December 25th, 2021, something changed. NASA launched the James Webb Space Telescope, a machine so technically advanced, so almost impossibly powerful, that the engineers who built it sometimes struggled to believe it would actually work. It was the most expensive scientific instrument ever placed in space. It took 30 years to design, build, and launch. It carries a mirror the size of a tennis court made of 18 gold-plated hexagonal segments that had to unfold perfectly in the vacuum of space, like the petals of a mechanical flower. One wrong move, one failed hinge, and $10 billion in 3 decades of human effort would have become the most expensive piece of space debris in history. But it worked. Everything unfolded perfectly, and the universe has not been the same since. Here is what most people do not understand about the James Webb Space Telescope. It is not just a better version of Hubble. That comparison is like saying a nuclear reactor is just a better campfire. Webb sees an infrared light, wavelengths of energy invisible to the human eye, wavelengths that carry information that has been traveling across space for billions of years, information that was hidden from every telescope that came before it. When Webb looks at a distant star and a planet passes in front of that star, something extraordinary happens. A thin sliver of starlight filters through the edge of that planet's atmosphere, and Webb catches it. It analyzes it. It breaks that light apart into its component wavelengths and reads what is written inside. Like reading the chemical fingerprint of a world that exists 40 light years away from where you are sitting right now. The system Webb has been studying most intensely is TRAPPIST-1, a small red dwarf star located approximately 40 light years from Earth, orbited by 7 Earth-sized worlds, a number that, when astronomers first confirmed it, caused a quiet but genuine eruption of excitement in the scientific community. 7 rocky planets, 1 star. And 3 of those planets sit in what scientists call the habitable zone. Not the maybe someday if conditions are perfect zone. The actual zone, the precise orbital band where temperatures allow liquid water to exist on a planetary surface. The same condition that makes life on Earth possible. Think about what that means. Not 1 planet in the right place. 3 of them. And here is where the story gets significantly more important. For years, astronomers looked at the TRAPPIST-1 system and asked the same foundational question. Do any of these worlds have atmospheres? Because here is the brutal reality of planetary science. A planet in the habitable zone without an atmosphere is not a habitable planet. It is a rock. It is a dead, airless, frozen, or scorched rock spinning silently in the dark. The atmosphere is everything. It is the blanket that regulates temperature. It is the shield that protects the surface from deadly radiation. It is the medium through which liquid water persists. Without it, habitability is a mathematical coincidence, not a physical reality. So Webb began working its way through the TRAPPIST-1 system, planet by planet, looking for atmospheres, and the early results were not encouraging. TRAPPIST-1b, the innermost world, showed no familiar atmospheric gases, appearing likely airless or hidden by opaque clouds. TRAPPIST-1c, another close-in rocky world, showed similar disappointing results. TRAPPIST-1d, despite being Earth-sized, rocky, and sitting in a region where liquid water is theoretically possible, was found not to have an Earth-like atmosphere according to Webb data. One by one, the closer planets were being eliminated. The list of possibilities was shrinking, but here is where it gets worse, or better, depending on how you look at it. Scientists had always known that the inner planets of TRAPPIST-1 were long shots. They orbit too close to their star, a star that is far more volatile than our own sun. TRAPPIST-1 radiates intense UV and X-ray flares, and it was even more active in its first billion years, during the exact period when its planets were forming and trying to build their atmospheres. Those inner worlds were bombarded, stripped. What Webb found on TRAPPIST-1b and c was not surprising to scientists who had run the models. It was heartbreaking, but not surprising. The real prize was always further out. The real question was always about the planet sitting 4th from the star, the one designated with a single quiet letter that carries enormous scientific weight. TRAPPIST-1e. Scientists regard TRAPPIST-1e as one of the most, if not the most, likely of the 7 TRAPPIST-1 planets to have an atmosphere and be potentially habitable. It is Earth-sized. It is rocky. It orbits within the habitable zone at a distance that gives it a shot at surface temperatures capable of sustaining liquid, water. For years, scientists built climate models around this planet, ran simulations, published papers, and waited for the one instrument powerful enough to actually look at it properly. And in 2023, Webb began doing exactly that, observing TRAPPIST-1e as it crossed in front of its star, capturing the faint transmission spectrum of light filtering through whatever might surround it. Using Webb's near-infrared spectrograph instrument, the team observed TRAPPIST-1e as it passed in front of its parent star 4 times between mid to late 2023. 4 transits, 4 opportunities for the universe to give an answer. And what came back from those observations, published on September 8th, 2025, in 2 peer-reviewed papers in the astrophysical journal Letters, is the kind of result that makes scientists choose their words very carefully. Because in science, the words you choose carry legal weight. You do not say confirmed when you mean strongly suggested. You do not say proven when you mean the data is pointing powerfully in this direction. You say tentative evidence. You say hints. You say possible secondary atmosphere. But read between those carefully chosen words, and what they are actually saying is this: something is there. Researchers have already ruled out a hydrogen-rich primordial atmosphere, pointing instead to the possibility of a secondary atmosphere, one that could sustain oceans or ice. A secondary atmosphere is not a relic from a planet's birth. It is built over time, through geological activity, through volcanic outgassing, through the internal chemistry of a living, geologically active world, pushing gases up through its crust and holding them in place with sufficient gravity. A secondary atmosphere means something happened on this planet after it formed. Something continued to happen. The planet did not die quietly. It evolved. And this is where everything changes. The data suggests the planet might have a nitrogen-rich atmosphere with traces of methane. Pause on that for a moment. Nitrogen. Methane. Those are not random chemicals. Nitrogen makes up 78% of Earth's atmosphere. It is the dominant gas in the air you're breathing right now. And methane. Methane is one of the molecules that biosignature hunters spend their careers looking for, because on Earth, methane in the presence of oxygen is produced overwhelmingly by biological processes. Life makes methane. Bacteria make methane. Wetlands make methane. Cows make methane. When you find methane in a planetary atmosphere, you do not assume life, but you absolutely do not ignore it either. Now, to be precise and fair, the scientists are careful. The planet could instead have no atmosphere at all, or an atmosphere obscured by clouds, and stellar flares and spots from the active host star contaminate the data, making it difficult to distinguish between different scenarios. The red dwarf TRAPPIST-1 is a troublemaker. It throws out radiation bursts that interfere with the very measurements Webb is trying to make, injecting noise into a signal that scientists are desperately trying to read clearly. This is the challenge. This is the maddening, exquisite difficulty of what these researchers are doing. They are trying to read the chemical composition of an atmosphere 40 light-years away, through the interference of a flaring star, with a window of observation that lasts only the few minutes it takes for a planet to cross its star's face. And yet, the signal is there, persistent, showing up across multiple observations, surviving the noise. The researchers note that while the planet likely no longer has a primordial atmosphere, there is tentative evidence for a possible secondary atmosphere. And an atmosphere, if it exists, would most likely be nitrogen-dominated. The research team at Cornell University, part of the JWST TST Dreams program involving more than 30 scientists from the United Kingdom, the United States, and India, is not done. An additional 15 transits of TRAPPIST-1e are underway and were scheduled to be complete by the end of 2025, using a different observing strategy where consecutive transits of both TRAPPIST-1b and TRAPPIST-1e are targeted, using the bare rock of planet B as a control to trace out the star's active regions, so that any excess atmospheric absorption seen only during TRAPPIST-1e's transits would be uniquely caused by the planet's atmosphere. This is elegant science. This is researchers designing an experiment that isolates the very variable they are hunting, stripping away every alternative explanation until only one remains. What most people are not seeing is the scale of what is being attempted here. This is not a minor academic exercise. This is humanity, for the first time in its entire existence, building the tools sophisticated enough to ask the question, does this specific planet, orbiting that specific star, have air? And actually getting an answer. Every civilization that ever existed before ours would have considered this impossible, not difficult, impossible, and we are doing it right now. But the TRAPPIST-1e story is only half of what Webb has been doing in its relentless search for other worlds. Because while one team of scientists was watching a planet 40 light years away cross its star, another team was attempting something even more audacious. Something that, if confirmed, would rewrite every textbook, every assumption, every map of our cosmic neighborhood that has ever been drawn. They pointed Webb at Alpha Centauri. Astronomers have found nearly 6,000 exoplanets orbiting other stars. But for every confirmed detection, there are countless mere hints, inconclusive observations that could just as well be blips of cosmic noise or glitches in a telescope. Most of these hints fade under scrutiny. Most of them, when examined more carefully, turn out to be instrument artifacts, background galaxies, or passing asteroids. Most of them simply do not survive contact with the truth. But every so often, one of these candidates is so tantalizing, so potentially transformative, that it cannot be ignored. And in August 2024, Webb produced one of these candidates in the most dramatic location imaginable, Alpha Centauri. A is not just any star. It is our nearest solar twin, a star almost identical to our own sun in both age and temperature, sitting just 4 light years from Earth. 4 light years. That is roughly 25 trillion miles, an almost incomprehensible distance in human terms, but in cosmic terms, it is our backyard. Alpha Centauri. A is the closest sun-like star to us that exists, and for decades, the burning question among astronomers has been, does it have planets? Because if it does, if a world orbits our nearest stellar neighbor, then everything about our understanding of nearby space, about the distribution of planets in the galaxy, about the prospects for interstellar exploration, shifts fundamentally. In August 2024, using an instrument called a coronagraph that blocks light from a star to enable astronomers to better see any faint planets in orbit around it, Webb's team counteracted light from both Alpha Centauri A and its companion star Alpha Centauri B to reveal an object over 10,000 times fainter than Alpha Centauri A itself. 10,000 times fainter. Think about what that means in terms of the precision required to detect it. You are looking at a star burning with the fury of a nuclear furnace, and you are trying to see something so faint next to it that the ratio between the two is 10,000 to 1. The technical achievement alone is breathtaking. And what they found was a blob of light, a faint, persistent infrared source sitting in a region approximately twice the Earth-Sun distance from Alpha Centauri A, placing it squarely within what scientists calculate as the star's habitable zone. The researchers published their findings, calling it the strongest evidence to date of a gas giant orbiting Alpha Centauri A. Not a hint of a rock, not a shadow of a small world. A gas giant, potentially a Saturn-scale planet orbiting in the habitable zone of the closest sun-like star to Earth. But here is where it gets worse, or stranger, or more mysterious, depending on your frame of reference. Additional observations of the system conducted in February 2025 and April 2025 did not reveal any objects like the one seen in August 2024. The planet was gone, not moved to a different position, not detected at lower brightness, gone. And the scientific community was confronted with something genuinely puzzling, a case of a disappearing planet. This is not a phrase scientists use lightly. This is a phrase that means we saw something real, we cannot find it again, and we do not yet understand why. The research team used computer models to simulate millions of potential orbits, incorporating the knowledge gained when they saw the planet and when they did not, trying to construct a scenario that was consistent with all the data. The simulations found that in half of the possible orbits modeled, the planet moved too close to the star and would not have been visible to Webb in both February and April 2025. In other words, the orbital mechanics of the system, the complex gravitational dance between Alpha Centauri A, its stellar companion Alpha Centauri B, and the potential planet, could explain why the object appeared in August and vanished in the follow-up observations. It moved behind its star, or it moved into the glare, or it traced an orbit so unusual, so shaped by the gravitational presence of 3 massive objects, that it only shows itself to us in particular windows of time. A 2019 sighting of a potential exoplanet candidate by the European Southern Observatory's Very Large Telescope was also incorporated into the simulations, and the models found consistency between that earlier data and the new Webb observations. 2 independent telescopes, 2 different years, 2 different instruments, both pointing at the same location around the same star and finding something. According to informed sources in the astronomical community, this is not the kind of coincidence that gets dismissed over coffee. This is the kind of coincidence that gets funded for follow-up. Researchers describe this as potentially the most significant JWST finding to date, noting that it would also be the first planet imaged around a star that matches the Sun in both age and temperature. The first. In 4.5 billion years of our solar system's existence, in 6,000 years of recorded human civilization, in 100 years of modern astronomy. This would be the first time we directly imaged a planet around a true solar twin. The real story is not just about one planet or one star or one telescope. The real story is about a species that is, right now, in real time, building the capability to answer the question it has always been too small to answer before. And the answers are coming in faster than anyone expected. And they are stranger and more tangled and more thrilling than the clean, simple confirmation everybody was hoping for. What most people miss when they read these headlines is the cumulative weight of what Webb is assembling. It is not finding one piece of evidence. It is building a mosaic. TRAPPIST-1e shows tentative signs of a nitrogen and methane atmosphere. Alpha Centauri. A shows a mysterious, recurring object in its habitable zone that appears and disappears according to complex orbital mechanics. A hidden super-Earth has been detected dipping in and out of its own habitable zone around another nearby star. The picture being built, observation by observation, paper by paper, is one of a galaxy that is absolutely full of planets. Planets in habitable zones, planets with atmospheres, planets orbiting the stars closest to our own. And yet, and this is the part that should keep you up at night, we are still at the very beginning. We are still in the era of hints and tentative evidence and carefully chosen words. We are still in the era of 4 transit observations. When what we need is 40, we are still using instruments that are revolutionary but not yet sufficient, making measurements that are extraordinary but not yet definitive. Every result Webb produces right now is the most detailed result in human history, and simultaneously not detailed enough to give us the certainty we crave. We are looking at these worlds with the clearest eyes we have ever had, and we still cannot quite see them clearly enough. Within the next 2 years, the scientific community expects to have a much better picture of how TRAPPIST-1e compares to the rocky planets in our solar system. 15 more transit observations using refined techniques combined with the control data from TRAPPIST-1b should tell researchers whether the atmospheric signal they are seeing is real or noise. The methodology is clever, the data is accumulating, and the answer, whatever it turns out to be, will be one of the most consequential pieces of information the human race has ever possessed. And for Alpha Centauri, the research team has hinted that more planet hunting is coming, with NASA's Nancy Grace Roman Space Telescope, scheduled to launch as early as May 2027, also being used to search for new worlds around our nearest stellar neighbors. Roman is designed specifically for wide-field astronomy, for surveying large regions of sky with unprecedented sensitivity, and its arrival will provide a second powerful instrument to train on Alpha Centauri and confirm or deny what Webb found in that single haunting August 2024 observation. 2 telescopes, 2 golden eyes, pointed at the same target, waiting for a planet that may or may not show itself again. This is not how science was supposed to look. Science was supposed to be clean. You observe something, you run the experiment, you get the data, you publish the result. But the universe does not cooperate with clean timelines. The universe hides things. It puts them in orbits that make them visible only sometimes. It surrounds them with flaring stars that contaminate your instruments. It places them behind the glare of their own sun at the exact moment you go looking. The universe is not withholding information out of cruelty. It is simply vast and complex and governed by physics that does not care about our impatience. What these scientists are doing, what Webb is enabling, is fundamentally new in the history of knowledge. For the first time, we are not theorizing about whether other Earths exist. We are not building philosophical arguments about the probability of life in the cosmos. We are pointing an actual machine at actual planets and reading their actual atmospheric chemistry. We are doing the experiment. The result is not yet conclusive, but the experiment is underway. And that distinction between asking the question and actually testing it is the most important transition in the history of human curiosity about the cosmos. Consider what it means for TRAPPIST-1e specifically. A planet 40 light-years away, Earth-sized, in the habitable zone, showing signs of a nitrogen-rich atmosphere with possible methane. If you built a checklist of conditions necessary for life as we know it, and started checking boxes, you would be checking them for this world. Rocky surface, check. Habitable zone orbit, check. Size comparable to Earth, check. Evidence of atmosphere rather than bare rock, tentative check. Nitrogen is dominant atmospheric gas, tentative check. Organic molecules like methane possibly present, tentative check. No checklist is a guarantee. No amount of boxes checked means life is definitely there, but the accumulation of compatible conditions on a single world 40 light-years away, detected by a machine we launched less than 4 years ago, is something that deserves to be spoken of with the weight it carries. Think about what that means for the next decade of astronomy. If the 15 additional TRAPPIST-1e transits currently being analyzed return a clear atmospheric signal, if the nitrogen-methane hypothesis holds and the stellar contamination is successfully accounted for, Then the conversation changes overnight. It shifts from could there be an atmosphere to what is in that atmosphere and what produced it. The follow-up proposals are already being written. The observation programs are already being designed. The scientific machinery is already spinning in anticipation of a result that could arrive before you finish your next year on this planet. And if the Alpha Centauri signal is confirmed, if Roman or Webb or some other instrument catches that faint infrared blob again, in the right place, at the right time, moving on the orbit that the simulations predict, then we will have done something unprecedented. We will have directly photographed a planet orbiting our nearest stellar neighbor. A planet, that is, by current estimates, somewhere in the mass range of Saturn. A planet potentially large enough to have moons. Moons that could, themselves, be candidates for habitability. The chain of implications does not stop. Each confirmation unlocks a new question, and each new question reveals a deeper layer of what we do not yet know. The universe has a structure to these revelations. It does not give you everything at once. It gives you a hint, then a signal, then tentative evidence, then confirmation, then understanding. We are somewhere in the middle of that sequence right now, past the hint stage, deep in the signal and tentative evidence stage, straining toward our confirmation. Every piece of data Webb returns is moving us forward on that sequence. Every paper published, every transit observed, every spectrum analyzed is one more step toward a moment that will likely arrive within our lifetimes. A moment when the question, are we alone, receives its first real evidence-based answer. But here is what no headline tells you. Here is what the mainstream science media buries in the final paragraph, or leaves out entirely. The question, are we alone, has two answers that carry radically different implications. If the answer is yes, if we are alone, if TRAPPIST-1e turns out to be a cold, airless rock, if Alpha Centauri has no planets at all, then the weight of that answer is almost too heavy to carry. It means that in a galaxy of 400 billion stars, in a universe of 2 trillion galaxies, something about Earth is so rare, so improbable, so cosmically unique that it has happened essentially nowhere else. That answer would change philosophy, religion, and human psychology in ways we cannot fully predict. It would make Earth not just our home, but our species' only proof that the universe is capable of producing minds that can look back at it and ask why. And if the answer is no, if TRAPPIST-1e has an atmosphere thick enough to sustain oceans, if there is something biological producing that methane, if life of some kind has independently emerged 40 light years from where you are right now, then the implications are equally staggering in the opposite direction. It means life is not a miracle. It means life is a process, a natural recurring consequence of chemistry and physics, given the right conditions and enough time. It means the galaxy is not empty. It means we are not special in the way we always assumed, but perhaps we are special in a different, more interesting way, as one of countless expressions of a universe that is deeply, persistently, unstoppably alive. Right now, as you are reading this, Webb is still out there, 1.5 million kilometers from Earth, sitting at the gravitationally stable point called L2, staring at the universe with its golden eye. It is cold, maintained at temperatures near absolute zero to prevent its own heat from contaminating its infrared measurements. It is alone, in the most profound sense, farther from Earth than the Moon, beyond any repair mission, beyond any human reach. But it is working. Every day it collects photons. Every day it adds data to the record. Every day the picture sharpens slightly. The answer may come from TRAPPIST-1e, it may come from Alpha Centauri, it may come from a planet nobody has thought to look at yet, orbiting a star that does not even have a proper name, in a region of sky that no amateur astronomer has ever pointed a backyard telescope toward. The universe does not tell us where to look. It only rewards us for looking. What we know right now is this. The instruments exist. The methodology works. The signals are appearing. The evidence is accumulating. And the scientists are not stopping. They are writing the next proposals, designing the next observations, building the next telescopes. The Nancy Grace Roman Space Telescope is coming in 2027. The extremely large telescope, currently under construction in Chile's Atacama Desert, will dwarf every ground-based observatory in history when it opens its eye in the late 2020s. The next generation of space missions is already on drawing boards, designed specifically to find and characterize Earth-like worlds around nearby stars, to measure their atmospheres, to search for the chemical fingerprints of biology. We are not at the end of this story. We are not even at the middle. We are at the moment just before everything accelerates, the moment where the tools become capable enough, the data becomes dense enough, and the evidence becomes convincing enough that the question stops being philosophical and starts being empirical. We are standing at the threshold of knowing. And the only question left, the one that no scientist, no telescope, no amount of data can answer for you, is what you will do with the answer when it finally arrives, because it is coming. Whether TRAPPIST-1i is alive or dead, Whether Alpha Centauri hides a world or only fooled us with light, the answer to the oldest question our species has ever asked is no longer a matter of faith or philosophy or imagination. It is a matter of time, and Webb is counting the seconds.